In the 01_read file project, you'll see that I've used this expression when I allocate some memory for the character array B. The char star here, between parentheses, is a typecast. You can think of it as being an instruction to the compiler to convert the type returned by the malloc function to a char pointer. At any rate, it tells the compiler that this is how you want to treat that value, so don't complain by showing warnings or errors, because believe me, I know what I'm doing. Of course, when you use casts, you need to be careful that you really do know what you're doing. For the typecast to be valid, the types have to be compatible. Now, let's look at a simple example with some numeric variables. Now here, I divide two integers, x by y. In C, an integer division by default returns an integer. Let's run this to see. So even when I assign the result to a double, which is a floating point number, the value is the integer that was returned. Here that's 4, followed by lots of zeros after the point. But that's not very accurate. To make the results more accurate, I need to cast the division. To do the cast, I precede the expression with the desired type. Here that's the double type between parentheses. So let me try that now. And run it again. So you can see that when I run this, the result is shown to a higher level of accuracy with all the digits after the floating point. But what happens if I want to display a floating point number as an integer? So here I try to display the double variable result as an integer using %d in printf, and that will show the original result variable which I've got here. And when I run it, this is what I get. You can see that doesn't show what I expected at all. Now to fix that, I need to cast this to an integer. Again, the same syntax, desired type in parentheses. This time I run it, and this time I get the result that I was expecting. So this time the floating point value has been truncated to the integer 4. Now, incidentally, you need to be a bit careful when using casts with expressions such as this one here. You might think, for example, that if you wanted to cast the result of this division to a double, it would make sense to put the entire expression in parentheses. Let me try that. Well, is that going to work? Let's run it and find out. In fact, when I do that, I lose the precision again. So why is that? Well, the reason is that the parentheses cause the division, the integer division, to be done first. And remember, an integer division defaults to an integer result. And here that's 4. And only once that division has been done is the integer result, 4, cast to a double. And that's why you see this integer 4 represented as a double with all the zeros after the floating point. But if I remove the parentheses, run it again. Now this time the integer x is cast to a double first, and then it's divided by y. And that's why I get a more accurate floating point result from the division. Now let's go back to my pointer cast, which you'll find in 01_read file. In this case, the type of data returned by malloc is defined to be a pointer to void. That is, it's a pointer to some unknown sort of data. And what I do here is I cast this to be a pointer to char. And you might remember, as I've explained before, that can be a pointer to the character at the start of an array of characters. That is, to the address in memory at which a sequence of adjacent characters is located. This typecast from void pointer to char pointer works fine, so both the compiler and I are now happy. And while on the subject of data types, you might have noticed that the items read variable, that's the one that's assigned the result returned by fread, that's been declared as being of the type size underscore t. Now size underscore t is not a standard C type like int or double. So what exactly is it? Well, according to the documentation of fread, and here I'm referring to the Microsoft documentation, the return value of fread is defined to be of numeric type, and that type is called size underscore t. But that still doesn't tell me what size underscore t really is. Now in order to find that out, I am going to use one of the search tools built into CodeLight. So I go to the identifier size underscore t, right click, and I select go to declaration. Now if you're using a different editor, you may have a similar tool available, so you might want to check that to find out how to navigate through code. Now this has taken me to a type def in the file stddef.h, which is one of the system header files. Now this here makes size underscore t an alias of this identifier. But what is that? Well, let me go to this identifier and search again. And now this takes me to this hash define, and I find that this is defined as long unsigned int. Now, don't ask me why these type definitions have been made. The history of the C language and its libraries is long and complicated, and all I can say for sure is that someone at some time thought that this was a good idea. At any rate, what my searches have shown is that the size underscore t data type is in effect a shorthand alias for the long unsigned int data type. Now, the C language recognizes a number of different integer types, some of which are signed, that is, variables may have either a plus or a minus value, and some of which are unsigned, so that variables can only have positive but not negative values. And some integer types may have different upper and lower values. That is, they may have bigger or smaller possible ranges of values. For example, a long may be capable of holding a bigger range of values than an int, though these value ranges vary according to the compiler and operating system. In most cases, a simple int will suffice for most things. However, when the C library defines a specific data type, such as the return value of fread, which is defined to be here of the type size underscore t, that's the type you should ideally use.